myself. And it's one of those things. It's one of those things too that, hey Matt, that you're going to find professions. All professions have something of this thing. You're going to have something. You're going to have a difficult week, a hell week of whatever your particular job is for whatever particular even positive reason, and you just have to recognize that as expectations go up, I am human, and therefore my attitude will probably go down. And you absolutely need to recognize that, especially when you have to deal in personal relationships and maintain those relationships and be responsible for them. The nice thing about being a kid right now is, to a certain degree, you can kind of just like void out your parents, go in your room and just kind of block out the world and go. I mean, not entirely, I know, but to a certain degree, you have that as a capability. Yes? Yes? I'm pretty darn sure if I do that with my son right now, okay, that's potentially a problem that's gonna get DCFS called on me. So,
DCF, what's that?
For negligence.
It's CPS.
Don't worry about it.
It's CPS.
DCFS is.
Well, it was funny. So my old job was DHS.
Sure. It's probably a different acronym in Oklahoma. So
Trust me.
all right, Matt, we already did the first questions. Sorry, buddy. Oops. All right. Nuclear fission. All right. So we talked last chapter about natural radioactivity in the form of alpha radiation, beta radiation, and gamma radiation. What you're looking at here is nuclear fission. So what happened when Einstein figured out that E equals mc squared, he realizes that trapped within mass is an incredible amount of energy. But he pretty famously said, it's a moot point, because to release the energy within the nucleus itself, within the mass itself, would take more energy than what we actually would get out. So you have to put in a nuclear energy, a fission's worth of energy, in order to get less than that out. Okay. What he wasn't accounting for is, as a famous documentary once said, is World War II, and a very famous physicist called, is it Madame Curie that's usually in that one? Usually equated to that. She's typically the one that typically does radiation, and in radiation, she of course found that when an object radiates, that the combination of the masses, as we talked about with Q values yesterday, are typically less than their original parts. And why are the total masses decreased? Because it has released energy, which is exactly what we're looking at here. We start with uranium, okay? Now, uranium can split into, you'll see X and Y up there, because it can split into a couple different combinations, which we'll talk about. But the most important thing to get out of this, and I want to see if the picture's up here, so I'm not trying to explain the picture and then going through it. Yes, okay. So the most important thing to get out of it is that to make it happen, uranium is, yes, unstable. But by bombarding a uranium atom with a neutron and putting that neutron into the nucleus, it makes it that much more unstable. Having extra neutrons inside of there, as you learned with carbon-14 versus carbon-12, do not make it more stable, it makes it less stable, more likely for stuff to kick out. So what you look at here is the neutron up here on the left side gets added to the uranium atom, and you'll notice that we still have uranium because the protons haven't changed. We have one more, so we skipped from 235 to uranium-236 just by adding one neutron. And this starred energy here is to say that it has a much higher energy, kind of like we talked about yesterday with gamma radiation. Those protons skipping to a higher energy level to fall down. The natural thing that happens as they fall down, and you'll notice the couple of yields here, because we have the first one, the neutrons just going in to yield 236 uranium, but the natural process with this uranium is that it splits apart into two different atoms, and now, most importantly, shoots out neutrons. Now, why is that important? Well, what caused this process was a neutron going into a uranium atom. So if that uranium atom also shoots out neutrons, this process becomes, at bare minimum, self-contained. Meaning, do you have to put in excess neutrons from the outside to continue the process? No, you don't. So, In this particular case, this example of X and Y, you'll see that the left side is exactly the same. They're not showing you the intermediate step of the middle 236 uranium, but just the final product. And just like we did yesterday with nuclear reactions, you'll notice that those top numbers, those mass numbers, are going to all add up to the same thing on both sides, as well as the protons right there underneath. But again, if we then add the mass of the left side, okay, you're going to get 236, and the right side you're going to get 236, just like we said. But if you actually look at the isotopes like we did yesterday, what you find is that mass is always lost. And as mass is lost, your average Q value, as you actually already stated in the questions, is about 200 mega eV. Now, if you don't know that it's 200 mega eV, or if a problem on your homework asks you to calculate that, it's the exact same process that we did yesterday. You would find the 235 isotope, you would calculate the neutrons mass as well in U. You do that on the right side, you find the difference, you multiply that 931.5. I didn't mention this yesterday. Typically 931.5 4 sig figs is the conversion that you typically use to get over to the other one. All right. So nuclear fission in a nutshell, this is just the visualization of that last page. You have a 235 atom in picture A right there. In comes a neutron, approaches the nucleus. The neutron is then absorbed by 235, making it 236 star. Remember that star, like you said yesterday, is kicking it up to an excited state. That excited state causes the nucleus to naturally deform and oscillate, like it says, like a liquid drop there, kind of just bouncing back and forth and split apart until you get two daughter cells, two daughter nuclei. Typically, it's like I said, it's not just the two that you saw on the last page. It's not just what's BA there? Is that barium and kryptonite? It could be a couple other combinations, which we'll see practiced a little bit later. But the other thing here is that other neutrons potentially come out in order to maintain this. And you'll see in this particular case, they have 3 coming out. Now, as that happens, as I mentioned, it sort of creates a chain reaction. Okay, we have 1 into the uranium, which splits into, you'll notice these daughter cells, just like we said, with barium and kryptonite. But then those 3 neutrons then hit 3 more uranium-235 atoms. And you will see, I think, at least 2 other combinations here. I think that's xenon and strontium. I could be wrong on strontium. What's it's going to bother me. 38. I was right with strontium. Xe54. Xenon is correct. So I was right about that one. Okay, Y39. Yttrium. And what is that? I is iodine, if I'm not mistaken. Yep. And then, is that neodymium? What's that?
I think it's neodymium.
You are correct. Niobium. Niobium is that one. And then 51 is antimony. Antimony. Which, of course, SV, but, you know, the Latin people and all that. All right, point being. Okay, point being, this growing number is potentially problematic. Okay, why? Because, as Aslan said, I jokingly said it wasn't that much energy, and it's not. A single atom only releasing 200 mega eV is not that much energy. But when it builds and builds and builds and builds, this is building exponentially, right? This first one's 200. This next one's 600. This next one, you're getting an idea, is 1800, and so on and so on and so forth. And you'll notice that the amount of energy coming out is getting larger and larger and larger and larger, and that's probably potentially a problem. Yes, because obviously if we leave this unchecked and it does it really quick, exactly right. What you are dealing with right now is literally a fission nuclear bomb. Okay, this is the process that a lot of people are afraid of. So, what happens at nuclear reactors? I've mentioned this before. Okay, a nuclear reactor is basically the same thing as a coal power plant. Do you remember what I told you? How you make electricity at a coal power plant? Steam.
Spin something.
Steam spins Specifically, magnets is what I was looking for. Yes, a turbine would be, yes. Steam spins a magnet. Nuclear reactors is literally the exact same thing. Steam spins a magnet. The only difference is how that steam is created, right? What's the problem with burning coal in creating that steam? Hurts the environment. We have other elements potentially coming out on the backside. The other problem is it takes a lot of coal. There's not that much energy in coal, relatively speaking, to the nuclear power that is contained within the mass uranium here. So all uranium is going to do is take that energy, is take that Q value and heat up the water to make steam. But once it's already made steam, does it need to keep building in the form of that energy? Does it need to keep building more and more and more energy once it hits? I mean, it needs to put in enough energy over time to keep it boiling, right? Just like setting a pot on a, excuse me, you set a pot on the stove and you need to keep putting energy in to maintain it boiling, yes? But there's a set amount of energy going in. It's not like it's building and building and building and building, because obviously too much energy, everything melts in addition to water, and that's not helpful. Yes? So here's what we have in this process, okay? If you look at this right here, what we have is inside water, you're gonna have the fuel element, this red box right here, that would be uranium-235. And then right next to it are control rods. These are some material that naturally absorb neutrons, okay? And they can track how good this potentially is at the process by simply measuring the temperature of the water. If the temperature is increasing, well, that means they've got too much energy going in past that, you know, if more energy is coming out past that boiling point, right? If the energy is falling, it's too little. And so this right here, this is called the reproduction constant, okay? Once they've achieved the correct temperature, what they're going for is a K value of 1. It is known as a atomic it sounds bad, but it's actually exactly what you want. It's a nuclear reactor going critical. This is correct. It sounds bad because of every TV show you potentially watch, but critical means K value is 1. What does 1 mean? Well, here we go. Like we said before, the average number of neutrons that actually comes out in one of these processes is 2.5, meaning 50% of the time it shoots out 3, the other 50% of the time it shoots out 2. Fair? If it shoots out 2.5, 1 went in and 2.5 went out, that means you are going to grow in how much energy is being produced. Yes? So, critical is when you've got that appropriate energy, you've got the water boiling, you just want to keep it boiling. What you really want is for every atom that breaks apart, only one neutron goes to another uranium atom. Now, obviously, you can't control how many come out, so what we do is we need these two to be absorbed. To absorb them, that's why we have these critical rods right here. Okay? So critical rods are there to absorb neutrons such that, ideally, once it's at the appropriate level, only one neutron goes to another uranium. If K value is less than 1, that means less than 1 neutron per atom is going out. So that means the amount of total energy is going to be decreasing. We don't have enough neutrons to maintain that same level. Okay? The actual bad one, because critical does sound bad, if you heard something like the local nuclear power plant has gone critical, you might go, that doesn't sound great. Okay, but it's just fine, it's normal. The bad one is actually if that power plant goes supercritical. Okay? Now, this does happen when you first get a power plant going because, like I said, you want that process to build and build and build and build. And they have systems in place to make sure it's good. In other words, they have these control rods to absorb neutrons. And basically, simplistically put, because there's definitely more here than even I know, basically you can control the K value simply by taking those control rods and lifting them in and out of the material. By putting it further in, it's going to absorb more neutrons, and you can track that by looking at the temperature. And they've got more control rods here than are even necessary. One of the major reasons why nuclear power plants are completely fine is if anything goes wrong in a half a second, click a button, control rods to the nth degree just go into the substance, absorbs every single extra possible neutron that could possibly be coming out, and it goes subcritical, and the nuclear process entirely stops and in fact naturally cools itself down. Obviously supercritical, if control rods got pulled out and people kind of entirely avoided monitoring the situation entirely, then yeah, it could go supercritical, and then yes, the material could potentially be in the form of a Chernobyl. All right, anyway. Big boom. Russia.
No, I'm.
My apologies. All right, so this is the process of fission, like we talked about. I think I've covered pretty much everything that I needed to on it. Oh, okay. So the other thing that I did want to say on this subject, and I think, yeah, they do actually talk about it. I'm going to go over to my other computer here quick. Sorry, Matt. I'm coming back. Can you hear me okay? Physics 2. Click. Let's go here. Physics 2.
Yeah.
Chapter 30. I hate the presentation of these slides just because they do these pictures and I know they want me to talk about stuff underneath, but I don't have it memorized. All right, so fission in a nuclear reactor's heat molten sodium or water. So actually, it's not just water, like I said, but it's the same process. Depending on the system, which is pumped into a heat exchanger, thermal energy is detached from secondary system. Water converts to steam, which of course spins a giant turbine, electricity through what was that? Faraday law that we talked about previously. Fission reactors are extremely safe. According to Oak Ridge National Laboratory Review, the risk of living 8 kilometers from a nuclear reactor for 50 years is no greater than the risk of smoking 1.5 cigarettes or drinking a half a liter of wine or traveling 240 kilometers by car, flying 9,600 kilometers by jet, or having one chest x-ray. So this is, of course, people doing actuarial tables that try to basically produce your life down to the statistic of dying to a particular thing. And they're saying that the likelihood of your risk is pretty much the same as one chest x-ray, which pretty much all of us will have at some particular level at some point in our life for various reasons. Like, I don't know if you were to play baseball and you were playing in left field and your coach told you that you need to try harder, so you said, oh, okay, I'm going to go for it. So you went for it. And the other senior that was in the other line did the exact same thing, and you said, I got it at the same time. Point of interest, I was technically center field. But you heard that, so you didn't hear the other person, and so you dove for the ball, and they dove for the ball. Their knee contact with your temple, and you were out for the next 4 hours, making you miss senior night entirely. You would probably get your chest x-ray or your head x-ray.
Like you were knocked out?
Yeah, 100%, like 4 or 5 hours. Yeah. While senior night was going on. Great news is my mom's an x-ray tech, so I woke up to her doing my CAT scan. Hey, how's it going? Like, this is not good right now. Anyway, I'm fine. Right. All right, this was like 23 years ago. All right. Junior year.
Oh gosh, you can't even remember.
At least it wasn't your senior night.
26.
Yeah, that's true. If you were a junior, who cares?
26 years now? Oh, it's my senior year.
Oh,
You
you
said junior
said
year.
it was your junior year.
No, I'm sorry. You're right. I said it was my senior year.
Things are reasonably fuzzy for the story.
Debunk.
Hey, the best
Touche,
senior
it was
night.
26
Best
years.
senior night.
And
Alright,
you
that
did
was
get
my
a probably
sophomore
heavy
year.
concussion.
Oh yeah. All right, moving on.
He did the
I keep saying 26.
Exactly.
16. I would have been
16.
sad. I would have been 8 if I said 26. All right, moving on. Safety issues associated with nuclear power reactors are complex and usually emotional and overblown. All sources of energy have associated risk. Coal, for example, exposes workers to health concern. This apparently was plugged by the nuclear power plant people, me just reading this slide right now. But they are pretty stupid safe relative to other forms of energy. All right, given concerns about greenhouse gases, studying alternative forms of energy production is extraordinarily important. Despite the advantages in technology can reduce cost, solar and wind power remain extraordinarily expensive and intermittent. And that's true. The amount of energy powered by one of these things is great, but the cost of building them by itself is vastly higher for the amount of energy coming out of them versus your standardized coal power plant. nuclear is, on the other hand, converts actually, there are breed reactors that convert nuclear waste in nuclear fuel, meaning the elements that you've actually already seen up here today, and can turn thorium into an isotope of uranium stable enough for using in a reactor. With that technology, current reserves would likely be sufficient for over 1,000 years. So that's if we never collected any more uranium whatsoever. Our current amount of it would be fine for the next 1,000 years if we kind of went in that direction. Obviously, as I say, nuclear power plants, you can already feel, probably within yourself, like either concern or a very good understanding of why other people are probably concerned. It's probably the word nuclear. Yeah.
Do solar panels use photoelectric effect? That's something like I
No.
kept meaning to ask and I didn't
Ish.
remember.
So, in chemistry terms, okay, the photoelectric effect. Yes.
Okay.
I thought you were saying, my apologies, photosynthesis. And that is true, ish. Both of them are a redox reaction, okay? And thus, but the photosynthesis is a stupidly efficient. We are nowhere close to the efficiency that photosynthesis does by itself in the form of, I mean, we'll just take it like this. A tree, you can think about the size of a tree and how much, leaves it takes in order to, power a tree. And we need vastly more surface area just to power a house, which is arguably actually less energy to power the house. But okay, I'm done. Next. The sun is a mass of incandescent gas, a gigantic nuclear furnace where hydrogen turns into helium at temperatures of millions of degrees. The sun is hot, the sun is not. Sorry, my apologies. So that was nuclear fission, uranium being turned into its daughter cells and reducing and the Q value. Okay, what we're looking at here is fusion. So there's fission and now fusion.
They made it very clear
They
to help people who
I
haven't
know. It's already annoying because I've made the joke several times about how physics is not great at naming things in the form of they name stuff like stupid plainly. And then they get to something like this, two processes that are relatively speaking similar. I mean, obviously they're in the same chapter and they call one fusion and one fission. That's a butt move. That's a butt move physics. All right, so great news about this reaction is you already know it. Two hydrogen turned into helium at temperatures of millions of degrees. Why? Based on what we've already stated, do these temperatures need to be millions of degrees?
So they're more active?
Nope. Yes, but no. Nope. Remember we talked about the sun is not hot enough to burn. Your idea of activation energy only applies if the sun was burning. It isn't. Come on, you got this within you. Why does the sun have to be hot in order to produce fission? Think about what I've told you fission actually is if it's not hot enough to burn.
Molecules quantum bumping into each other. It's the electrons.
Where's this process taking you? Keep going. It's not the electrons, it's the protons.
The protons.
And it's not that they're moving really fast.
They are moving really fast. Why do they need to be moving really fast? It's not, okay, it is they're moving really fast. That's not to give them the necessary oomph to slam together. Because what we said is two protons essentially traveling 99.999 the speed of light are not going to have enough kinetic energy to get close enough to overcome the Coulombic effects that would repel them. That's what I mean to say when the sun is not hot enough to burn. Okay?
So,
not to burn. But fission is not burning. Remember what I said. Why do they need to be moving fast?
So like the probability is super like
A higher number on the bottom of what you remember is de Broglie wavelengths. A de Broglie wavelength is based on Planck's constant divided by mass times velocity. So a larger velocity makes a smaller wavelength. So to get that wavelength going anywhere near close to each other, so that's what must be that good. Actually, no, that's not good. Them getting smaller is not the part that you want. Them getting close enough to each other, that they had any sort of chance whatsoever of overlapping. Actually, you would want a wider wavelength for smaller, but with a lower velocity, they're not getting anywhere near close enough that those two probability functions have even a minuscule percent chance. So you get them fast enough that they get close enough, those wavelengths overlap, and there's a low percent chance that hydrogen is inside the other hydrogen, yes.
The sun is like on fire, right?
No, it's not fire.
What is
Plasma.
why is
Plasma.
that? Okay, yeah, okay.
Yeah.
Okay,
A plasma in simplistic terms. So you have a gas, molecules are essentially unaffected by each other. They're just going around running into each other. Okay. Liquid, remember that you've got your nucleus and you've got your electrons, and therefore if I've got like a water, I've got the nucleus over here, and it's slow enough that this nucleus can hold on to the other's electrons. If it was going too fast, they just skip off of each other, right? That's steam. Okay, once you make it fast enough, aka heat it up, okay, then it's fast enough to skip out and jump on its own. So they roll over top of each other. Okay, so those are obviously gas and liquid. Now, why don't they interact with each other? Because it's going too fast. But what if it was going too fast for Coulombic effects, positives and negatives to hold on, but if there's enough mass there, then gravitational, despite being ridiculously weak, would be strong enough to hold it in place. So you have a gas that has the energy of a gas, but not held in place by Coulombic effects, positive and negative attracting, but is held in place by enough gravity to make it actually act a little bit more liquidy, aka plasma. All right, so two light nuclei form a heavier nucleus in a process called fission. So if you want simplistically, fission, I said that poorly, that one was fusion, I think I said the other one. Fission, big thing becomes smaller things. Fusion, okay, for any of my Dragon Ball Z fans, is two smaller things becoming a bigger thing. Don't get the Dragon Ball Z reference, you make me sad. All right, all stars, ha, right, two smaller than.
Okay, yeah.
Anyway, yeah, all stars generate energy through the fusion process. About 90% of stars, including our sun, fuse hydrogen. Some older stars will actually form helium into heavier elements, which is just insane. That requires a humongous amount of gravity. The energy produced by fission inside increases the pressure inside the star and prevents the star from collapsing due to gravity. So if this wasn't on, the star would just collapse in on itself. It has that much gravity, and thus, as it collapses in on itself, there would be a huge amount of mass in a very, very, very small place, otherwise known as a black hole. All right. Two conditions must be met before fusion in a star can sustain its energy needs. So it's got to be, and we basically said this. One, temperature has to be high enough, aka they have to be moving fast enough to get close enough. And second, the density of nuclei must be high enough to ensure a high rate of collision. It's like I said, for this hydrogen to be inside of the other hydrogen, does it happen always? No. There is a very, 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 very low percent chance it happens. But when can you be positive that a very low percent chance is assured? When it happens a lot. So there's a high enough density that low percent chance will happen enough to basically be self-sustaining. Now, this process is relatively assured for stars because they start from natural causes. You have hydrogen all over the place. What is hydrogen doing to other hydrogen? Attracting, because all mass has gravity. So it attracts all the hydrogen in the area and all the hydrogen in that area. It starts coming together, starting off as a nebula or a gas cloud. But eventually it starts pulling in more and more and more. Especially it's going to happen quicker because there's more mass in the middle, there's more dense. And as it pulls it, what's going to happen to the speed of these hydrogen as they're coming in? They're going to increase. And so naturally over time, due to gravity, the density will go up as well will the speed of these until eventually fission clicks at the correct density as well as the correct speed. Like I said, and I've said this 1,000 times, but this is the way they put it. In fact, temperatures inside the star are not high enough to collide protons to overcome Coulombic repulsions. Not hot enough to burn is to say these are not going fast enough that these positives would not always, 100% of the time, repel each other if we were not dealing with quantum tunneling. All right, so fission, there it is, fusion in the sun. 2 hydrogen eventually become, and this is I think it's a 3-step, 4-step process. In the first process, 2 hydrogen slam together, and you'll notice what do we have up there? The very first situation is called? That is beta decay. And that second particle there on the right side is? That is a positron, right? Which is the opposite of the electron. It is the electron, just the positive charge. And you'll remember the antiparticle of a positron has a neutrino coming off as well. Then you're going to have the daughter product of, you see the deuterium up there, okay? A deuterium is just a hydrogen with what?
2
Almost.
2 neutrons. One
neutron,
yeah.
correct. Just with the neutron in it. Deuterium is just basic, but it also means it's technically twice as massive. That deuterium then interacts with other hydrogen around, and you'll notice forms helium in gamma radiation. Now, why is that helium now? Or actually, more importantly, on that first situation, why did it not become helium to begin with? See if you remember the beta particle conversation from yesterday. If you'll remember, and you'll see this again in just a minute, okay? Oh man, I just realized that Jacob is missing this day of all days. He's going to be disappointed. Anyway, you will note that the bottom part does not match the proton level. It should become helium, except if you remember, a neutron, okay, a neutron can split apart into an electron and a proton, or it can split apart into a positron and an antiproton. Yes? And what does that antiproton do?
Kills the proton.
Correct. So one of the neutrons up there should actually destroy and create a proton and all the fun jazz that you have sitting right there. And then the deuterium interacts with the hydrogen, like I said, to form helium. One thing you'll notice about that helium is it is missing a neutron to be its standard self. And we have one more here. We have hydrogen and that helium will once again form another helium, but again with beta decay. So actually there is a 4th process that will also happen. So what you see here is that the leftover, let's see if I can't do this well. This leftover guy comes into that interaction, which is going to form with hydrogen, which is naturally abundant in the sun. This helium gets put into this reaction, but could also go, if it's abundant, into if I've got 2 of them right here, in which actually 2 helium-3 molecules become a helium-4 along with 2 hydrogen. And you should be able to follow the math on this. Top is 6, bottom is 4, bottom is 4. Yes? Now, what you'll notice is, okay, you might say, well, does that make this self-sustaining? Because we're producing hydrogen, right, which is used in that process. But if you track the overall, you will see that it took 1, 2, 3, 3 of those to make 1 helium-3. Yes? And so it would take 6 to make 2 helium-3s. Yes? So overall, it would take 6 hydrogen to create those 2 while only producing 2 in the process. So I think they're going to do this one in just a second from the beginning to the end, but let's see if you add them all together. If you track all those interactions in this is talking about a fusion reactor, isn't it? Okay, so this is specifically from the sun. But if you track all of these from the beginning to the end, essentially what it comes down to, simplistically put, very simplistically, these are all the total ones that can do it, is you get 2 hydrogen into 2 helium. But you got to know that other stuff is going on there, because if I just put 2 hydrogen into each other, does it actually give us the necessary numbers to form 2 helium? No. If I put 2 hydrogen together, I would have 2 on the top, 2 on the bottom. Okay. All right. Here we go. Is that all I was supposed to say about that one? So energy is thought to be created in the sun and other stars through what's known as the proton-proton cycle. For this cycle, being in our sun, 4 protons come to form an alpha particle, 2 positrons, and 25 mega eV of energy is released. The first 2 steps shown, where D stands for deuterium, which you see up there. The second reaction follows either a hydrogen-helium fusion or a helium-helium fusion, which you said. The liberated energy is mostly carried away by gamma rays, positrons, and neutrinos. Gamma rays are rather quickly absorbed by the dense gas, which raises its temperature. Positrons combine with the electrons to produce gamma rays, which are also to be absorbed by the gas before they travel more than a few centimeters. The neutrinos, on the other hand, almost never interact with matter, so they escape from the star, carrying out about 2% of the energy generated with them. These energy-liberating fusion reactors are called thermonuclear fission reaction. The fusion, the hydrogen or fusion bomb, first exploded in 1952, is an example of an uncontrolled thermonuclear fission reaction. The great deal of effort has been gone underway to develop and sustain collectible fusion power reaction. Controlled fusion is often called the ultimate energy source because of the availability of water. What nice thing does water have within it?
2 hydrogen.
2 hydrogen. Okay. For example, if deuterium, the isotope of hydrogen, consisted of a proton and a neutron, were used as fuel, 6/100ths of a gram could be extracted from 1 gallon of water and cost about 4 cents. This means that fuel cost of an even inefficient reactor would almost be insignificant. It would cost us practically nothing to produce this particular energy. The additional advantage of fusion reactors, I can almost guarantee you that the advantages and disadvantages of fusion and fission stuff are going to be on the test. So if you're not copying this down, please make sure you get it in here. Make sure you get it out of the textbook when you read through it. An additional advantage of fusion reactors is that comparatively, very few radioactive byproducts are formed, as opposed to fission, which produces radioactive isotopes all the time that then have to be discarded. Here, the end results of the fission process are a gas that we like to use at parties, an inert gas that makes your voice sound funny.
And aren't we running out of it?
We're not.
Okay.
More
It's
concise
fake
than that.
news.
Well, there's a good bit. I think Neil deGrasse Tyson was on a podcast and spoke about this in about 2 minutes, much more eloquently than I could. So look him up and he'll tell you why it's not. But, all right. Unfortunately, a thermonuclear reactor that can develop a net power output over a reasonable time period is not fully yet in reality. Many problems must be solved before a successful device is constructed. The fusion reactors that appear the most promising is the construction of a fusion power reactor involving 2 isotopes of hydrogen, deuterium and tritium. You'll remember tritium is the hydrogen with 2 neutrons, or a mass number of 3. These reactions shown here have a Q values that refer to the amount of energy released per reaction. As we've already discussed, deuterium is readily available in unlimited quantities from lakes and oceans that are extraordinarily inexpensive to extract. Tritium, however, is radioactive with a half-life of 12.3 years and undergoes beta decay to helium-3. For this reason, tritium has to be artificially produced because it is not natural. It is not naturally occurring. Fundamental challenge of nuclear fission power is to give the nuclei enough kinetic energy, which naturally occurs in the sun from just heat, right? Obviously, we don't have that kind of capability here. So we have to give it a kinetic energy to overcome Coulombic forces in close proximity. This step can be accomplished by heating the fuel to extremely high temperatures, like 10 to the 8th Kelvin, 10 to the 8th Kelvin, far greater than the interior temperatures of the sun. Why would ours have to be hotter than the sun?
Because you can't get it. We can't get it in much stuff.
Correct. We are not going to ever be able to develop the level of density that the sun has, as it's kind of big and has a lot of gravity. And we would like to prefer the gravity of 9.8 meters per second squared. The step can be accomplished by higher temperatures. Such high temperatures are not easily maintained in a laboratory. That is an understatement. Or power plant. At these high temperatures, atoms ionize, and the system then consists of a collection of electrons and nuclei, commonly referred to as plasma. So, fusion reactions that appear the most. I said that one, right? Nope, I didn't. A fusion reaction. Yeah, I did do that one. Okay, this is what I wanted. Yep. All right. There are two other caloritic factors. Don't ask me what caloritic means. I have no idea. That determine whether the thermonuclear reactor will function. One is plasma ion density, which we discussed. Two is plasma ion confinement time. So what you're looking at here is this idea that, all right, what if we took a plasma and maintained it in, you'll notice right there, that is just a solenoid. Okay, so we put a high degree of electricity or current through there, okay, and AC current. So you're dealing with changing magnetic fields within that particular material, okay? So Lawson's criterion states that the net power output of a fusion reactor is possible under conditions shown on this slide. The problem is the plasma confinement time is not yet solved. How can plasma be confined at a temperature of times 10 to the 8th for orders of greater than 1 second? Most fusion experiments use magnetic field to confine the idea of plasma. This is the sentence I wanted to get to, and then I'm just going to walk away from this. One device called a tokamak has a donut-shaped geometry, a torrid, which you're looking at right there on the board, as shown in the figure. The device used the combination of two magnetic fields to confine the plasma inside the donut, and a strong magnetic field is produced by current in the windings. The weaker magnetic field is produced by current in the torrid, and the resulting magnetic field lines are helical. In this configuration, the field lines spiral around the plasma, preventing it from touching the walls of the vacuum chamber. So this is their theoretical understanding of how we can potentially get fission to take place here on Earth at a reasonable environmental temperature without having the same level of density that they have. And if you've heard conversations relatively recently, this has always been pursued. You can imagine if any company freaking figured this out ever, they ultimately become the richest company easily, because we get rid of, like, this device is actually not that large. If they could figure out a way of safely doing this, all electricity grids disappear. All batteries disappear. Everything run on this would take a process that takes 4 cents to the gallon, so you would probably have devices inside your house that would do this naturally, and it would take basically pretty much every house no longer pays money for electricity, no longer pays money for energy. Cars powered by this particular process don't really require very expensive fuel in the slightest. All electricity becomes basically ridiculously cheap to produce as such. All right, I said this is going to go quick, and that took a while. Luckily, this next part goes pretty quick, because I'm guessing you don't need me to spend a lot of time on this slide.
Yeah.
I've never seen this before in my life.
Unfortunately. All right, so I've talked about this before. Strong force binds neutrons and protons together in the nucleus. Electromagnetic force binds atoms and molecules. We spend time. And basically weak force, I don't think I actually mentioned this. The weak force is the principles belonging to the specifically beta decay that occur in the radioactive chapter last. So we have technically discussed all 4 of these, and obviously gravity. Gravity is mass attracts all other mass. I know I have told you the relative strength before. I know you know which one the strongest one is, but essentially let's do this. If the strong force has a power of 1, okay, the electromagnetic force is on the order of times 10 to the negative second, meaning 1/100th of the strong force. The weak force is times 10 to the negative 6th compared to the strong force in size. And that long-range force called gravity, we actually did this math at one point in time, is times 10 to the negative 43rd relative to the strong force.
Would you
Again,
say electromagnetic was?
times 10 to the negative second.
Wow.
All right, we're going to go really darn quickly through this next one, although I do want to briefly touch on the second slide here. So, elementary particles and fundamental forces. You know how we said that light is essentially a photon, yes? What did I say light was previous to that? A wave of what?
Energy.
No. A wave of
It's like
what is waving?
Or no.
Electric field and magnetic field.
yeah. Okay.
So, prior to this particular point in time, okay, what we would have said is this. If a proton exists here, then if I pop it into existence, then exhibiting outwards would be a electric field. Yes? And thus a proton sitting here, let's say they both pop into existence, would put out their respective electric fields. How fast do they go? Speed of light, because that's what light is. So I could figure out these 2 protons would not immediately affect each other, yes? They would have to get affected by each other's fields. This is what we would have said prior. But we've now also learned that light and electromagnetic radiation can also be seen as a particle, specifically a photon. So think of it from this perspective. Rather than think about a proton pops into existence here, okay, and then the electric field affects this proton here. The way to think about this in terms of elementary particles is that every force has a particle that transfers its energy. The proton pops into existence here, watch this, here we go, shoots out a photon. And then what happens to this guy? This would get hit that photon, and thus since it got absorbed that photon would, just basic pinball mechanics, would shoot that way. So previously we would say an electric field pushes it that way. Now with particles we can say this guy shoots a photon over here which pushes it this way. Same result just from the perspective of particles. And while that's going on, this guy is shooting a photon at this guy, and so what do 2 positives do to each other? Repel. Okay, so why then would a positive and a negative attract? Well, rather than hit and bounce the other way, it's the opposite, so it pulls it inward. Anyway, it absorbs. But here, basically, the photon. Highlighting. Come on, there we go. The photon is the particle that basically where the electromagnetic force gets used on. Okay, gluons are called the strong force particle. Bosons. Somebody asked me previously what a boson is the particle. W and Z bosons are used for the weak force. And gravitons are the particles used for gravity. Essentially what I just explained was this process. You have 2 electrons kind of bound towards each other. What you're looking at right here is what's known as a Feynman diagram. They were invented by, as you would imagine, Richard Feynman, which you saw up here. He lived from 1918 to 1988, and yes, we are getting stupid close to when we currently exist. He created these in around the 1960s, so about, where were we at now? About 60 years ago now. This is called a Feynman diagram, and as you see on the left side, time is going up, and what we're seeing here is two electrons directly affecting one another. That an electron goes there. The reason it's called a virtual photon is because the photon would be created by one side but absorbed by the other, so it would cease to exist. You would basically have a net result of no photons in this particular process. This electron comes in, up and right. This electron's coming in and left. They get close enough that we would normally say they repel because of Coulombic forces. This thing, the elementary particles would say it is the photon that gets going to the left and to the right that force them to rebound back in the opposite direction. I know that's not enough, but this is the chart of essentially information that I just told you. I already gave you the relative strength of all of them in order. Range of force, both electromagnetic and gravitational, are long in that they follow the inverse square law, or they can technically go to infinity, technically, because at a certain point they're so close to zero they basically do nothing. But, and then you'll notice that the strong and weak forces are in fact limited in range, like we talked about. The strong force between the neutron and photon are at the order of femtometers, and you'll notice that the weak force is even smaller than that, at the order of times 10 to the negative third femtometers, or I believe that's attometers. All right. Positrons and other antiparticles, and I've got basically 2 slides and we're done. No, that's not true. I've got 5 slides. Okay. In 1920, the theoretical physicist Paul Dirac, who lived from 1902 to 1984, developed a version of quantum mechanics that incorporated special relativity. Dirac's theory accounted for the electron's spin, magnetic moment, but had an apparent flaw in that it predicted negative energy states. The theory was rescued by posting the existence of what's known as an anti-electron, having the exact same mass of an electron, the opposite charge we've already talked about, called the positron. The general and profound implications of Dirac's theory is that for every particle, there must be an antiparticle with the exact same mass but the opposite charge. Antiparticle is usually designated by having a bar over the symbol of the normal particle, but in the case with the positron, that's not the case. You just write the E and you put a positive up to symbolize like you see here. But most of them, like you're seeing with antiproton and antineutrino right there, you just put a bar over their regular symbol. Practically every elemental particle has distinct antiparticles, except for the photon and the neutral pion, which are their own antiparticles. In 1932, a positron was actually discovered by Carl Anderson, so a little less than 100 years ago. We have discovered these particular particles. In the cloud chamber experiment, to discriminate between positive and negative charge, Anderson places the cloud chamber in a magnetic field, which, as you well know, causes negatives to go one way and positives to go the other. So this causes moving charges to follow circular paths. He knows that some of the electron-like tracks deflect in the opposite direction. Thus, they must be the exact same mass because they go through the same circular radius. But since they go the opposite way, it means we've confirmed that they have the opposite charge. Oh, I'm sorry, that was this guy right here.
What stuff are we looking at?
This is I don't know. My guess is the experiment.
Well, yeah, but I mean, like, I don't understand like what the cool part about it.
I don't know.
Okay.
When a particle meets an antiparticle, they are annihilated and results in a high energy photon. This process of electron-positron annihilation is actually used in the medical diagnosis technique of positron emission therapy, or PET. The patient is injected with a glucose solution containing a radioactive substance that decays by positron emission, just beta decay. With the example, for example, oxygen 15, nitrogen 13, carbon 11, and fluorine 18. The radioactive material is carried to the brain because blood eventually ends up in the brain. When a decay occurs, the emitted positron annihilates with an electron in the brain tissue, resulting in 2 gamma ray photons. With the assistance of a computer, the image can then be created of sites where glucose accumulates, because where the glucose then accumulates is where you're going to get a lot of these particular collisions, and then they can assign those collisions a particular colored value. So you'll see in this particular case, a lot of collisions are occurring at the yellow sections, or even at a very high density case where the orange sections are at. From images, a PET scan can point to a wide variety of disorders in the brain, including Alzheimer's disease, because glucose metabolizes more rapidly in active areas of the brain than other parts. PET scan can indicate which areas of the brain are involved in various processes known as language, music, or vision. So you can have somebody consume this, basically hook up to a brain analyzer, and then start playing music or play. And then, of course, high activity is going to be where you have a high amount of glucose. Glucose is going to be directed to these areas, then telling us essentially which areas basically get super amped whenever you're playing music, whenever you're doing. Sorry, that's a technical term. I apologize. All right.
Super amped.
All right. So, what am I looking at here? A giant table of some particles and their protons. You will notice things that you are familiar with. Starting on the upper left corner, the leptons. The electron, or the electron neutrino, okay, are up there on the upper left side. Those are symbols that you definitely recognize. The muon neutrino, tau, and tau neutrino, you're probably a little bit less familiar with, although we did discuss muons being created in the upper atmosphere regularly in our conversation on special relativity. Skip down towards the bottom and the baryons, and you'll start to see the proton and neutron, and obviously you know those. But now we have the lambda, sigma, xi, and omega. Okay. Now, I think a couple things to notice on why you may or may not have heard of some of these numbers is if you skip across the value, you'll see, of course, it's antiparticle in the next column, which is usually just the same symbol with a bar over top of it, except in the case of some where they say self, where they are their own antiparticle, meaning they run into themselves and annihilate. You'll see some weird columns in the middle of B, L, E, L, mu, L, tau, and S, which we'll talk about in just a second. And then just to the right of that, you'll see kind of the reason why we typically talk about some particles and not others. In the form of the electrons, you'll see that the electron and the electron neutrino are stable, meaning they do not naturally decay within our lifetime, and they're gonna stick around for us to detect. Whereas the muon, as previously discussed, has a half-life of about so this is even its lifetime, my apologies, this is not even its half-life. 2.2 times 10 to the negative 6. Or at the bottom, you'll notice that the proton is interestingly stable, but if you go right beneath it, and very interesting subject is that the neutron isn't. So I'm not going to touch on that right now, but I'll let you go forward into that in the future physics classes. Besides the particles transmitting forces, basically we classify these particles into two big categories. Hydrons and leptons, according to their reaction. So you have hydrons are composed of quarks. Leptons are thought to be truly elementary, so leptons being at the top up there. Okay? Particles that interact with the strong force are called hadrons. So the top are leptons, the center, the hydrons there, hadrons rather. And hadrons, hopefully you see, are divided into two camps. The mesons and the baryons. So why do you not usually hear these particles in normal physics? Because you have to get really, really, really in-depth into the strong force, which we spent like 4 or 5 slides just to understand the generic basics of before if you decide to continue forward, which we're not going to do here. All right. So what you will then potentially see, 2 more slides in a minute, is this. You'll see this reaction between hydrons, and what you have there is, I don't even remember, so let's do this. Let's look back over here to see what we got. We have a pi negative, which is the antiparticle of the pion. This is the antiparticle of the pion, becoming the muon, not the anti-muon, just the standard muon, okay, which you'll notice on the upper left corner right there, in combination with an antineutrino. These are interactions that happen. And then we see the muon become, hey, I know all of these. You should have the last part of these memorized. The right side of that is a electron added to a antineutrino. Okay. So what you will potentially be asked to do with a situation like this is potentially be asked, these are just some examples of the leptons, but you saw them on the previous slide. The electron, the muon, the tau, and the neutrino. I think it's called a muon. It's an electron neutrino, a muon neutrino, and a tau neutrino is what I think they're called. But you can see them kind of right next to their respective parts. What you might be asked to do is ask, do they follow the conservational laws? I believe these are on homework. So, what are the conservational laws? Well, these are values that we have found that must be maintained in order for a collision to occur. The law of conservation of the baryon number is, as any conservational rule, the sum of the baryon numbers before the process must equal that after the process. So where do you get the baryon numbers? That would be the B value on the left column right there, in that that's highlighted. You'll notice, and hopefully this makes sense, for the most part, baryon numbers are exclusive to the baryons at the bottom of the thing. The baryons being that category of protons and neutrons that you're very, very used to. So the other experiment is the conservation of the electron-lepton number. The sum of the electron-lepton numbers before the decay and after the decay must be the same. So here what we have is we have a neutron yields a proton plus an electron plus an antineutrino, which we have already talked about. This is the basic process of beta decay, that a neutron can become a proton. Now to check this, you go, all right, how many leptons does a neutron have? Well, you go over here and you go neutron. Okay, how many leptons does it have? Well, 0. It has 0 leptons. Okay, all right, good. So that must mean the total must be 0. So then you look at the other particles. What's the lepton number of the proton? Lepton number of the proton is also 0. Okay, we're good. But then you'll see the electron, and the electron, hopefully this makes sense, has an electron-lepton number of 1. Okay? So then you have to go, all right, what do I need to complete this? Well, the antiparticle of these always have the opposite lepton number. So here we have the lepton number of the electron. The electron neutrino is -1, and you can see that here. Okay, that the neutrino is 1, but like I said, the anti is always going to be the negative of that. Now, I'm really just worried about these two first columns right here. There are other conservational laws that deal with these other ones. There's the electron-lepton number, which is that first column. There's the muon number, which must be conserved. There's the tau number that must be conserved. And you might have heard this previously. This little guy right here is the quantum quality of strangeness, which is a little bit redundant at this particular point in time. But it must also be conserved in these particular processes. I am not expecting you to do anything major. The thing that I would expect you guys to do is be able to do this. Which of these can and cannot occur? And what you do is, yeah, absolutely. It'll be absolutely available. This chart will be available to the test for you to look up. So I'm not going to do it right now unless you guys really want to practice with it. But it's just these type of things. And they're definitely on your homework. And there it is, the conservation of strangeness, which, as you can look at here, I'm not going to mess around. And I'm done.
Sweet.
With the entire book.
It's done. We're done. We can never come back. Except for the test, Thursday. That's never it.
Well, the quiz Thursday isn't actually.
Yeah, that's right.
Sometime.
Oh, yeah.
Next Tuesday. Next Wednesday. Forget we have Monday.
Oh, we have Monday off?
Cashmere Pulaski ginger.
Who doesn't love that
And
red
then,
guy, that white
and then a
tie?
week from Thursday.
I emailed her. The whole reason she posted next week's schedule was because I emailed her. I was like, where's?
All right, I'm done. When do you guys need those recommendation letters done?
Today.
I know.
Oh, I'm gonna do extra so like just by the end.
I'm not.
Okay.
I gave it up to a couple other people.
I want to do all three of yours, okay? Because it's only fair with what I've asked you to do.
I can come.
I have Rebecca's letter done, so it's going to be a quick transition for her. I need to do the other two of yours. I planned on doing it in my prep period, and Bannister came and we had an education conversation. So, sadly, I wish I was just having students do work next hour, otherwise I would work on that. But
Okay, I was gonna say like
So
I could
it's
come
gonna
and
have
pick
to
it up
be-
6 hour.
if I'm not distracted in tutoring, it's going to have to be by the end of tutoring, which I'll try to have yours done by. Otherwise, I can scan it and email it to you to print. Will
Okay.
that work? Where do you need to take it by the end of the day? I'm sorry for giving you this logistical problem. I should already have it done.
It's okay. It's
Postal office 5 p.m.
What's that?
Postal office 5 p.m.
By the post office by 5
You
p.m.
don't think it
Yes.
that's the mountains?
Okay, that'll be fun. We're going to make things interesting.
Half of
I don't think it has to be that step. I think you just have to write like a quick little,
There's like a
and then
character
It
chart.
does for me.
Okay.
It's a self.
He's not gonna underdo it.
It's a self-imposed struggle.
Texas.
I was gonna say.
Oh
like,
shoot! No! Sorry. Just real quick.
He's
Because
not
why
done.
would we do all this and then not get to this? So skipping that one, skipping the freaking 8-way fold, it covers up dimensions and time space. Quark model. Okay, so leptons are elementary is the fundamental belief, meaning there's the belief that there's nothing smaller than that. But baryons and hadrons are made out of particles themselves. Okay, those particles, as you're looking up here, come from the numbers of the baryon numbers. So these are quarks and antiquarks. Okay, meaning that a proton is made out of smaller things called quarks. Or to give you a couple of examples, okay, seeing the chart right here, you can see that their charge is not fully elementary. Okay, so while we say a proton and electron have quantized charge, that's not entirely true if you go down to the quarks, which can be split up into thirds or negative thirds or 2/3, and the total baryon number that you got from the last time. So if you remember, the proton has a charge, of course, of E, positive E, okay, and has a baryon number of 1, okay, as does the neutron as well. So if you look, it is a combination or understood of these guys right here and their respective antiparticles, okay, that create the proton and the neutron. So if you go to the next slide, you get this idea right here, okay? A neutron right here, down in the bottom right corner, is comprised of 1 up and 2 down quarks. Meaning, if you look at an up, if you get an up particle, you will get positive 2/3, but a neutron isn't supposed to have a charge. The down particle has negative 1/3, so 2/3 plus 2 negative 1/3 ends with the neutron having a charge of 0. And it is this idea, the combination of these quarks, that if the quarks then split apart, give us a better understanding then of why an electron and a proton can be created out of a neutron. Because a neutron is a combination of quarks, so splitting up these quarks in the correct fashion gives us an electron and a proton. I thought they were going to do proton. Oh, they have color on this. Where's the electroweak and standardized model? Yada, yada, yada. I mean, this is the combination of all the ideas that we have essentially said. The 4 fundamental forces, the respective things, and the particles that specifically come off of the back of those. This guy, primordial fireball, that's this one. This, of course, is I believe these slides came out before CERN, if I'm not mistaken. So I don't think that is CERN. I think I'm missing.
It says third in the corner.
Well, I'm going to go ahead and guess that it's CERN. Yeah, that's fair. Yeah, that would be that's the particle accelerator that runs in a circle over in Europe.
How did they find it as last chance to do that?
They cared enough to do it. Oh, here, I'm sorry, my apologies. Here it is. A proton is up, up, down. Okay, a neutron is up, down, down. Okay, and if you want the Konami code, It's up, down, left, right, A, B, A, B, story.
Yes.
No, I think this is where, I'm pretty sure this is where Konami got their original idea of the order of the Konami code is the core. All right, anyway, so, yeah, so up, down, you'll notice up. 2 ups would be 4/3, with the down, -1/3, to of course give it the charge of positive E. And you'll notice that up and down both have a positive 1/3, so adding 2 of one and 1 of the other will always give you a baryon number of 1, which both neutrons and protons have. Anyway.
I can't.
Now this gets into other numbers, and these numbers essentially equate. You might say, like, where do these things come from? I reiterate that so much physics at the top is done from an experimental, trying to be like, well, maybe this is why we see this happen. And so a lot of these conservational rules are them going, well, we see this happen. How can we justify that this one happened, and this one didn't? And the idea comes out of this, all right, well, baryon number must be conserved. Strangeness must be conserved. And then you can start to get up into the charmed value must be conserved, and bottomness and topness of the up, down, strange, charmed, bottom, and top respective quarks, and all their anti-quarks as well. I'm done. I'm sorry. I'm done, Matt. I hope you enjoyed this. I'm trying to see if there's anything else I missed very quickly. Nope. Primordial fireball stuff. The idea behind dark matter, dark energy in the accelerating universe, sure, why not? The evolution of flat rate of the universe, the belief of Big Bang versus a closed universe, which is what we currently believe is the green thing, versus a flat universe versus an open universe, which we do not currently believe, based on blue shifting that we see regularly, problems and perspectives we're not going to get into, we're done with physics. All right, bye, Matt.